So this chromatogram will show you the result of the compound, which you can quantify it and identify it, all right? So it's very important in the industry. To be honest, as I mentioned, I provide consultation to the industry company, right? They actually use HPLC to detect any contaminants or not. I think you all know that halal issue is very serious. They want to detect whether the food is contaminated with non-halal component. So they need to run HPLC to detect. And also it's very important to identify the nutritional composition. We need to know how much the protein, how much is the carbohydrate, everything. And then at the same time, it used as a quality control where they use it to know how much is the microbe, is there any production of the lactic acid by the bacteria, all this thing, and also to prevent any faulty. So they want to ensure that the food is authentic, is true, and lastly to compliance with the food safety regulation. So I believe in Indonesia, you also have the food law and regulation. So when they need to run this kind of analysis to make sure that the product is compliant to the regulation, right? So the application is quite wide, but I'm gonna categorize it into right? We also need to detect the contaminant, like for example, the pesticide residue in the fruit and vegetable. You can detect as well. So we can use to detect toxin, like for example, the mycotoxin or alpha toxin in nuts, which is widely used in industry. We also use HPLC to detect certain, the chromatography to detect certain aroma and also the volatile compound, like for example, in coffee. So we know that coffee had different grade, different quality. So which one is the best coffee bean? So we will detect the aroma compound. The one that give the strong and persistent aroma taste will be the good quality coffee bean. All right. So of course, we also use chromatography for preservation. Like we want to know whether there is a addition of the preservative or not, because sorbate and benzoyl are very common preservative. So they will use that sometimes the industry will add acid, the amount is too much, which is not healthy at all. So what they do is that then we need to detect if the sorbate and benzoyl amount exceed the safety limit, then the company will be you'll get the penalty for this. All right. We also can detect the degradation rate. Like for example, in honey, how do we know that it's a good honey or bad honey? So you can run the chromatography method to detect a HMF. HMF is something we don't want it in the honey. So if let's say you detect the HMF in the honey, meaning to say your honey is already degraded. It might be degraded over time or due to the storage or everything. All right. Last but not least, of course, we use to check the authenticity. So we want to check every like for example, olive oil. So is there any other mixture of other plant oil, or is a pure virgin olive oil or not? So these are all the method we use to know whether it's authentic or not. All right. Next, we will move on to the principle. So I believe just now through the Mentimeter, you guys already have the basic knowledge about the chromatography principle. But I will quickly go through with you some of the important principle that you can use in the application. All right. So I will move on. First is the partition. So partition as the name part, all right, part
I'm so
meaning to
sorry,
say,
the listen wait. Someone raise their hand. Can
sorry.
suggest someone raise her hand. So maybe Izzy can ask
Uh-huh.
you a question first.
Okay, thank you, Miss
Okay,
Anjet,
sure.
for.
Okay, okay. So
I'm so sorry. Can you repeat the part of how can we separate, or how is the concept about chromatography in separation of this one aroma or volatile?
All right. So in aroma, we usually use the gas chromatography. So you need to know when we have the aroma compound. So this aroma compound is volatile. Volatile meaning to say it's very sensitive. Whenever there is a heat, this compound will evaporate as a vapor. So in the coffee, what we do is that we will take the coffee bean and then we will roast it. During the roasting, we will capture the vapor released from the coffee bean. All right. So this capture is called SPME. We use the solid phase methyl acetal to capture all these volatile compound, and then we inject it into a gas chromatography. So the gas, which will not react with the vapor, will bring the volatile compound throughout the gas chromatography column, so we can detect how many peak inside. So if the coffee bean have the volatile compound that is very strong and it can stay longer, usually this coffee bean is considered a good quality coffee bean because it can retain and is strong. It will not destroy easily. So this is how we grade the coffee
Saya
bean.
sayang.
Yes?
No, it's okay.
So what is the unit of the volatile things?
It can be a ppm
Okay.
part per million, yeah. Usually it's a part per million. So our nose is very sensitive actually. So we can actually detect sulfur. Sulfur, you all know sulfur at part per billion, meaning to say a little bit of sulfur, our nose already can detect it. So if let's say in the ppm, which is slightly higher than ppb, so our nose will feel like a trigger by this volatile compound. So that's why people are nowadays they will addicted to the coffee, because this volatile compound will tends to trigger your nose and the sensory part of your nose. Yeah. Okay.
Okay, thank you.
All right. Okay. So now I move on to the principle part. So I will just mention the 5 important principles that you guys need to know lah. So for the partition, so part, as the name mentioned, part meaning to say you split it into a different part, right? So it will separate based on their solubility in 2 different parts. So these 2 different parts should be immiscible, meaning to say they cannot mix together. So usually in the stationary phase, we will use a liquid that is coated, okay, coated on a solid. So you have a solid that is coated outside with a liquid, and then we will use a mobile phase. The mobile phase can be a gas or can be a liquid that stay over the column, right? So this the compound that you want will separated based on how they distribute in between these 2 parts. So meaning to say the compound that you want will be separated between A and B, but this A and B cannot mix together, right? Okay, so the advantage of having this is that it's very sensitive. You can handle a lot of compound. You can handle both polar and non-polar compound. So this is usually used in gas chromatography and HPLC for both volatile and non-volatile compound, right? So you need to know when you want to decide on the method, you have to think first, you want to use normal phase or reverse phase. So the difference between normal phase and reverse phase is that for normal phase, your stationary phase is polar, but the mobile phase is non-polar. But for the reverse phase, your stationary phase is non-polar, but the mobile phase is polar. So to cut it short, okay, you just look at the result here. Okay, the result here. For the normal phase, okay, the mobile phase is non-polar, meaning to say the compound that is non-polar will go out first. So you can see that A will come out first, followed by B, followed by C, followed by D. So A will come out first because A is non-polar. It will come out together with the mobile phase. So the polarity of the compound is D is higher than C, higher than B, higher than A. So in normal phase, those that is not polar will come out first. So with this setting, you can use to apply with those compound that is non-polar. Like for example, oil, palm oil, and also beta-carotene. As any vitamin usually is non-polar, so you can use that in the setting of the polar normal phase, except vitamin C. because vitamin C is polar. So you can use you can use the reverse phase, where for the reverse phase, the mobile phase is polar. So the polar will come out together with the mobile first. Imagine the mobile will move with the polar compound together. So D, which is higher polarity, will come out first, followed by CBA. So when this kind of setting you will use, when you know that the compound that you target is polar, like for example, caffeine, vitamin C, these are all polar compound. So you can use this method. So you have to, generally, I would say you have to decide first, what is the target compound. Then you study about target compound. If your target compound is polar, then you can use the reverse phase. If your target compound is non-polar, then you can use the normal phase, right? Okay. So this is an animation to show about the partition. So as I mentioned, you have a particle with the solid, and then outside of this solid, there is a liquid. So this solid and liquid is the stationary phase, right? So this solid, usually we use silica. In the market, we use silica because it's the cheapest. So this solid, all the silica will be packed inside this chromatography column. So this is your column, all right? Then when you have this column, you can start to inject your sample. So your sample have the triangle and also the square diamond shape. So indicate different polarity. So when the mobile phase, okay, you can run through, when you use the mobile phase to run through your column, this mobile phase will go through all the stationary phase, and then you can see that if the compound, let's say triangle, it will interact more with the aqueous phase, okay? The diamond will interact more with the mobile phase, so the diamond will move first, okay? So you can see that when we pump in the mobile phase, the diamond will move first because the diamond is carried by the mobile phase. After the diamond move already, then the triangle will move later on. So you know that the mobile phase is play a very important role. If your mobile phase is polar, then the compound that come out first is polar. If your mobile phase is non-polar, then the compound that come out first is non-polar. So this is what is so-called partition. So after you done the separation already, right, you can actually collect the fraction. So this is called fraction. So this fraction is depending on the time. So in this case, we collect the diamond first. Then after that, we collect the triangle. So in this every single test tube, this is your compound of interest. So this compound of interest, we also call it fractions. So you can use this fraction to do the application. Like for example, you collect the fraction enzyme, then you can use it, apply in the food setting. Okay. So this is a partition. All right. Okay. So next principle I'm going to share is adsorptions. So from the name, you know that adsorption is based on the compound adsorb to a surface. All right. How the compound adsorb to a surface of the solid stationary phase. In this case, usually we use silica or we use alumina. Alumina is more expensive than silica, but in the industry setting, it's very useful to detect the contaminant. So in the industry, we still will buy the alumina, right? So the mobile phase can be a liquid or gas that carry the sample throughout the stationary phase, and the separation is based on the polarity and the surface affinity. So the advantage of this method is that it's very simple and it's very not very expensive. It's good for separate the non-volatile, okay, non-volatile compound, and usually it's very fast, okay. So in this adsorption, your stationary phase usually is a solid, which we can use a silica or alumina, but your mobile phase, it can be something that is non-polar or moderately polar. So this method usually is used for non-polar setting. So it's better your mobile phase is non-polar, right? Like you can choose methanol, hexane, ethyl acetate. These are non-polar. If let's say your mobile phase is water, water is very polar. Okay, it's not so suitable to be used for this application. So what we do is that this compound, they will attach to your stationary phase and then they will move slowly. Okay, you can see the band here. I'm not sure you can see my pointer or not. Okay, so the band here is your sample, so it will move slowly. So those that is not absorbed to the surface will move very fast. Okay, but those absorbed to the surface will move very slow. Like for example, you go to a shopping mall. If the shop is very attractive to you, then you will go to the shop. So you will move very slow. All right, but those shop is not attractive to you, you will move very fast. Then meaning to say you don't have the interaction. Okay, so this for this setting, the polarity is very important because those compound that is very polar will tend to absorb to the stationary phase. So the mobile phase that you use should be non-polar to carry out the non-polar compound, right? So this is a video to quickly show you about absorption chromatography. So when you have that chromatography, usually you need something to absorb the compound. So in this case, it's called adsorbents. Adsorbent is something that can absorb your compound, all right? So the absorption will happen, okay, when you have the compound, let's say these three are your compound, and then this compound will attract to the adsorbents. So the attraction is due to the bonding. So we have different type of bonding, like for example, van der Waals or hydrogen bonds or any interaction bonding. So this compound will attract to the adsorbents, okay, through this bonding. So the adsorbents that we use usually is silica. So this silica is so special because they have the silanol group. So silanol group is also known as SiOH. So this group can help to attach to catch all these compounds. All right. Okay. So different sample, of course, they will have different binding capacity to these adsorbents. So when the mobile phase pass through the compound itself, those compound that has less interaction with the adsorbents will move first. Those compound with a very strong interaction with the adsorbent will stay here, right? So that is how the mobile phase wash away the compound, right? So this is how the adsorptions chromatography used, okay? So the next one is ion exchange. So just now we already talked about partition, adsorption. So another one is ion exchange. To be honest, ion exchange is a bit more complicated and it will need a little bit more understanding about the chemistry because it involves the charges. So this technique is usually used based on the attraction between positive charge and negative charge. So you need to know your compound very well because you need to know what is the charge of your compound. Let's say your compound is negative charge, then you need the positive charge to carry it out. So these are the things you need to study first, right? So the benefit of this method is that it is very sensitive and it's very selective, meaning to say we only choose the compound with a specific charges, right? And it can use for both inorganic and organic ion. So even though your sample is very complicated, it can use to separate, right? So for this ion exchange, usually the stationary phase, okay, contain the ion exchanger group. So just to let you know that for ion exchanger, we have two types, okay? When we use ion exchange technique, we have two types. Just like I told you that you need to know your compound first because you will decide which type you want to use, all right? So if your sample, okay, is a positive charge, if your sample is a positive charge ion, then you can consider to use a cation exchanger. So the cation exchanger meaning to say they have the they have the background which is a negatively charged, okay, then it will attract the positive ion. Okay. If let's say your compound, your target is negative charge, then you can consider anion. So anion exchanger is a positive charge where they will attach or attract those negative ion. So this is your stationary phase. But for mobile phase, of course, usually we will use an aqueous solution. Aqueous solution meaning to say water together with the buffer or salt. Okay. So the mobile phase, you can use the water and buffer and salt, right? So this ion, your sample ion, will bind to the resin based on the charge. After that, you can wash them out with you can change a pH, or you can change a buffer, you can change the salt to wash out the compound, right? So just like I mentioned, you have two types, depending what is your target. So let's say you want to work with the cation exchange, then you can use, you know that your functional group is sulfonic acid. This is a common functional group. And then your stationary phase, you can choose the sulfonated polystyrene, right? So for another one is anion exchange, okay? Then this is use the functional group quaternary ammonium. And then your stationary phase, you can use the quaternary ammonium resin. All right. So these two are different ion exchanger. But the concept is that you will have the positive charge attract the negative charge around the anion exchanger. All right. Meanwhile, for the cation exchanger, you have the negative charge will attract the positive charge around the exchanger. Right. So this animation is going to show you about ion exchange chromatography. So basically, ion exchange chromatography is based, like I mentioned, it's based on the attraction between two different charges. All right. So let's say you have a stationary phase with positive charge, you will attract the sample, which is the negative charge. Right. So it is usually used, to be honest, it's usually used for the separation, like protein and peptide and nucleic acid and all these things lah. So this is a common application of the anion exchanger. So the anion exchanger, as I mentioned, there are two types. So one is called cation exchanger, the other one is called anion exchanger. So the cation exchanger, will have the negative charge, all right? And then the anion exchanger will have the positive charge. So meaning to say, if let's say it is I'm not sure why my screen keep jumping. So if let's say you have a negative charge, then you know that you will be attract the positive charge ion. If let's say you have a negative charge, you know that you will be attract to the positive charge ion. So this is how it works, right? Okay. So just now I will talk about this. Okay. All right. Sorry. Next one. So I mentioned anion exchange you use to separate based on the charges. So one of the common application of this anion exchanger is that it will use in the protein. Okay, because you all know that protein, the structure that have 4 different groups. So usually the change of the protein will have the group, whether it's polar or non-polar, with the positive charge or negative charge. All right. So for separation of protein, commonly we use ion exchange. So it can be applied even though like the DNA, enzyme, vaccine, all these things, we can use this method, right? Okay. So for the you have to understand the principle is that at isoelectric pH point, okay, there is no charge. So if let's say your protein is at the isoelectric pH, there is no charge to your protein. But the protein will change their charge when you shift the isoelectric pH. So if you change the isoelectrical point, okay, the pH will change then you will have the net negative charge. Okay. Oppositely, if let's say your pH is moved down the isoelectric pH point, then you will have the net positive charge. So you will play around with your sample with the isoelectrical point. So when we talk about ion exchanger, many people think that it's very complicated because you need to know the isoelectrical point first. Then only you play around the charges. You want to adjust the pH up or you want to adjust the pH down, all right? So if let's say you adjust the pH above the isoelectrical point, then you will have a net negative. So it's negative, right? So it's advisable to use the anion exchanger because it's a negative charge. So it's a positive charge, so your negative charge will attract to the positive charge. If let's say your sample is 1 unit below the isoelectrical point, then your sample will be positive charge. Then it's advisable to use the cation. Because the cation is negative, then it will bind to your sample. So this is the principle behind it, all right? The main principle. So you have to understand the isoelectrical point of your sample first, right? Then you can run through the mobile phase. Then you can change the pH to remove the compound out. So this is how the anions exchange works. Okay. All right, so next I move on to the size exclusion. So for the size exclusion, normally people call it gel permeation chromatography, or we call it gel filtration. All right. When you look at this principle, size exclusion, you know that it's separate based on the size. Okay. Why am I keep jumping? Okay. So it's separate based on the size, right? So the compound, let's say your sample, have a mixture. So the molecule have different sizes. So when you know that your compound has different molecular size, then you can consider to use size exclusion method. So what happened is that they will separate based on the size, where the small one will go through and the large one will retain. All right. So the large one will come out first, then the small molecule will take longer time because they already go inside the porous stationary phase, right? So the benefit of this method is that it's very gentle. They will say that it's very gentle because your sample will not be disrupted. You can remain your sample. So it's very good to use for protein or enzyme or cell culture and things, and very simple. At the same time, most importantly, you can estimate what is your molecular size, all right? So for this method, for the stationary phase, you will have the column with all the porous bit, okay? Porous bit is like this, okay? This is the porous bit, okay? And then the bit you can use, like for example, agarose, polyalkylamide. But of course, agarose is the cheapest. You can usually in the industry, we will use agarose. So for the mobile phase, usually we will use a suitable solvent. Usually it's water. Then the separation is based on the ability of the compound to go through the porous stationary phase. Okay, so the large molecule cannot go to the pore, so they will move up. The small molecule will go to the pore and then they will delay. They will come out later. Like for example, this picture here. All right. So you have your sample. So the sample is the red color and the blue color mixture. So inside the column, there is a porous bit, okay? Meaning to say the bit inside there is many holes. So when you run your sample, okay, the small sample, which is a small molecule, will be trapped inside the pore, okay? It cannot move, be trapped inside already. But the large molecule will move out first. And the small molecule, because it's trapped inside, it will move out later. So you can see that the movement is due to the introduction of the solvent, meaning to say we keep on pumping the solvent into the system. So when you get the chromatogram, you can see that the large molecule will come out first, and then the small molecule will come out later. So this is the principle of size exclusion. All right. So to make you understand, you can also refer to the animation here. So this is a technique where the gel is inside the column, okay, where the gel will act as a stationary phase, and the gel consists of the porous bit, okay, so the porous bit. So sometimes we use gel, okay, so that's why it's called gel permeation chromatography, right? So this gel is a stationary phase with the porous bit. So you can use different type of gel. You can use polystyrene, dextrane, agarose, just like I mentioned, or polyalkylamide. So usually I will recommend to use agarose because it's a cheaper and cheapest and very durable, right? Easy to handle as well, right? So what you do is that you need to know that in this chromatography, you will have a total volume. You need to estimate how much the volume that you use. You will have a total volume, okay? So this total volume is the volume of the gel together with the inside